Welcome to the physics video lecture. This is physics 4B video lecture 21. And we are talking about magnetism, a new chapter called Sources of the Magnetic Field. And this is an amazing subject matter. I usually have some demonstrations that I won't be able to show you guys this time around. But let's go ahead and get started. So, sources of the magnetic field. In particular, we want to be independent of little chunks called magnets. So, what else can cause us to have a magnetic field present? So, sources of the magnetic field, write that down. And I'll just start with recall what we know about magnets and currents. So magnets and currents. Well, we know that a magnet somehow acts on a current carrying conductor, or if you just want to represent a current as a charge moving through space, it acts on that as well. So suppose we have a current carrying conductor. Here's current I coming from somewhere, going somewhere, and we have the north pole of a magnet right here. So yeah, we have some field lines coming out like this, and we have the law F equals IL cross B. So for some little segment of this here, what do we have for IL cross B? So we do the cross product, and since I'm going counterclockwise, apparently there's a force on this wire coming out of the board. And that's what you'll actually see. I actually have some demos that I could show you. I'm just going to describe it. If I have a magnet here, for example, that big powerful magnet I showed you in class the other day, and I run a current carrying wire through it, it flips over to one side as soon as I turn the current on, okay? So, the force acts on a current carrying wire. So, force on a current carrying wire. Now, here's another way to look at this. Okay, force on current. Another way to look at this is, what about Newton's laws? Newton's law would tell us that there's an equal and opposite force. So if there's a force on this wire due to this magnet, we should be able to say there's a force on the magnet due to the current carrying wire. We have that. So let's go ahead and write that down. By Newton's third law, there should also be a force exerted on the magnet, right? Equal and opposite. Okay, so there should be a force exerted on the magnet. There is, in fact, I'll put an exclamation point there, there is, in fact, a force. And a way to understand it is that force that's going to be exerted on the magnet is due to the fact that the current carrying wire generates a magnetic field. Okay, that's one of the most important discoveries ever, that you run a current through this wire and it will generate a magnetic field. And you can tell it generates a magnetic field. You'll hold some compass needle, you'll take this magnet away, hold some compass needles around here, and they will be affected by the current carrying wire. Okay, they'll orient themselves in certain ways. So that can now be formulated, and it takes a lot of experiments to determine the magnitude and the direction and all of that, and I will skip those experiments completely and write down the law. So Newton's law should be this, and we find, and should I put the find that a conductor that's carrying a current produces a magnetic field. Current carrying conductor produces a B field. And we have to write the formula down for that magnetic field. And it goes by the name of the Biot-Savart law. And we're going to spend a little time talking about this because it's kind of complicated. So the magnetic field, we're going to look at an infinitesimal element, and it's due to an element of current. So I'm going to skip the magnetic constant. I'm going to write it this way. Mu naught divided by 4 pi times R. So those are just constants, and I'll discuss them presently. I ds, so a vector infinitesimal element crossed into a unit vector that points to R, I'll draw this, divided by R squared. So this is, and I'm just going to write, there are different ways of writing this. There's also a K, a magnetic constant, just K sub M, but this thing plays such a role here, the permeability of free space, that I'm just going to introduce that. So what do we have here? Mu naught is equal to 4 pi times 10 to the minus 7. And if you look at the units here, there's going to be Teslas here, amperes here. So we have Tesla meter per ampere. Okay, Tesla meters per ampere. This is called the permeability of free space. Or you could just call it the magnetic constant if you want. And there are different combinations of these. You can look them up in the book. Permeability of free space. See, it has 4 pi built right into it, interestingly. Tesla meters per ampere. Okay. And notice this R hat is dimensionless, right? That's a unit vector, R divided, R divided by its magnitude. So that's a vector dimensionless, so you have, meters over meters squared. So Tesla meters per ampere. Good. So let's have a better look at this thing here. By the way, this is the Biot-Savart law. Law. We'll put it in a box and try to understand what it means. Because there's a lot of directionality going on here. We have this vector product. Best way to look at it, and the one we're most concerned with, is just a long straight wire. Actually, before that, for comparison, we have E for a point charge. Electric field of a point charge. So there, what do we have? We have Q over 4 pi epsilon naught, and then the directionality is just, we could just write R hat, okay? I'm sorry, 4 pi epsilon naught R squared, and then the direction would be a unit vector, okay? So just in terms of the dependence, right? Up in here, the numerator, we have a unit vector. You could say IDS gives us a piece of charge per time. Okay. But we also have an R squared dependence in terms of distance, okay? Inverse squared law. So yeah, we'll put that there. And we have this constant here, which is discovered just by doing force experiments in the lab. And we're going to see that this constant too can be discovered by doing force experiments in the lab. Okay, so much for that. This was just in parentheses. Let's go ahead and look at this law. Suppose we have a straight current. Well, actually, we'll start with we'll start with something not exactly straight. Okay, so there's a current going through here, and we have just some point P here, and let's take the force due to this little segment. Okay, so this would be our IDS. This is our little ds infinitesimal vector element, part of the current. The R hat is pointing here. This is R hat. The distance, let's use red here. The distance to this point, of course, is R, right? R hat is the unit vector that just gives us the direction. So that's what's in there, R squared ds R hat. And having said that, what is this cross product? Well, ds cross R hat means that the field is coming out of the board at that point. Okay, it's coming out of the board, and remember, with a cross product, the resultant is always perpendicular to ds and to R hat. So if we're over here with a ds, and then we would have an R hat that way. Again, the cross product would be out of the board, perpendicular to this current. So this current being in the plane means that that contribution is also going to be out of the board. And to get the entire E field due to this wire, you would have to integrate along the entire wire, whatever it's doing. Okay. So that's for explanation of the Biot-Savart law. Okay. That's referring to that law up there. So what we want to do next is get the field of an infinitely long straight wire. So let's just call this example. And then the next thing is B field of an infinite long wire. A long straight wire. With a current, obviously. Okay. So we have a long straight wire. There's our current. Okay, I'm separating it off from what we did here. And we have point P again. By the argument I just gave, that B field is out of the board, and we have to integrate, from minus infinity to plus infinity. And I have that integration here, but I'm just going to formulate it and give the result. So first of all, B is going to be the integral of all of these here. So we would have mu naught over 4 pi integral, and then this, well, we've got I as well, we can pull out. And then this ds cross R hat over R squared. And it's not that bad. It takes some trig substitutions, but when you do that cross product, you're always the magnitude of this, the direction's already been given, is always going to be a projection, projection onto that distance here. So if we call this distance A from the wire to our point P, where we're going to find the field strength, I'm actually going to just write it out. It's an important result that we'll use quite a bit. So, like I said, direction coming out of the board, just as on the argument up there. So if we carry out the entire integration operation, I'll just write here magnitude is B is just equal to mu naught I over 2 times pi times that distance A. A is the distance from the point, perpendicular distance to the conductor. So that's doing the integration. It's a nice integration. I think it would be in our text as well. I have it right here, mu naught over 2 pi A. But let's look at this result. That's the field of a long straight wire. If I draw it, here, let's, once again, example. So suppose this long straight wire this time is oriented like that. You can take the directionality there, and remember, this is just for the perpendicular distance. So if you look at it in this way, you're going to see that there are circular B fields. Circular B fields with the direction like that, or let's do a top view. So the top view, we would have the current coming out of the board, that's I, and we would have these B fields going in circles. That's just a consequence of this vector product and actually just this analysis right here. So here I is coming out of the board. So top view, I out of the board. Right, let's write that. Coming out of the board, so the long straight wire, we're looking down on it. And you'd have these concentric circles for the B field, or the field lines. What would actually happen if you held compass needles up to here, your compass needles would orient themselves along these lines. I'm just going to describe an interesting demo that we have that I can't show you. We actually have a long straight wire. It doesn't have to be infinitely long. It's about this long. And we have a plexiglass plate. So what we do is sprinkle iron filings on the plexiglass plate with the long straight wire coming out, and the iron filings will arrange themselves in little circles. Okay, so compass needles would also do the same thing. Iron filings do, and that's the proof that that's the field of a long straight wire. A is this distance from the wire, so the further out you get, the weaker the field gets. Okay. So, yeah, this is a tremendously important result. And the way to remember this is with the right-hand rule. So, yeah, I almost forgot that. So, note right-hand rule, of which there are a lot when vector products are involved. Right-hand rule is that the current is your thumb, and you're grabbing a wire just like I'm grabbing this ruler here. The current is my thumb, and my fingers are the direction. Okay, the fingers are the direction of the B field. That's the right-hand rule. To get right-hand rule for the direction of current and the magnetic field. So this is the basis of all manner of interesting applications. Of course, we don't just stop with a straight wire, but the straight wire is the basis. If we do an integration where we wrap a wire in a circle, we can also apply that integral with a very basic result that we're going to look at, I think, next. Let's make sure we've covered that. No, not quite next. One more thing here. So we're going to stay with this field of a long straight wire and its orientation, and then discuss the force between two long straight wires. So if I have two rulers representing the long straight wires and I have currents in them, they can experience an attractive or a repulsive force. And that's our next topic. I think I'll leave this up here because it's good to have that formula. This was the magnetic field of a long straight wire. Top view, this view here, these concentric circles. And I'll go ahead and erase this and continue on. So this will be called the force between two parallel conductors. Magnetic force between two parallel conductors. C-O-N. Conductors. So let's just set them up here. And why not just have I1, I2 separated by A, and ask what the force is going to be. So what we'll do is we'll say, what's the force on the one due to the other? So we'll consider the force on I sub 1 due to the field of I sub 2, right? They're both carrying a current, and I've drawn the currents to be parallel. So what do we have here? We have the conductor on the bottom producing at the top here a B field out of the board, not into the board. So the B field here is out of the board. Okay. So that's B, I'll call that B sub 2 out of the board. And then what is our force law? Force equals I L cross B. So here's IL pointing here, and I'm going to cross it into B, which is this way, cross it that way, and what do we have? That's turning something this way, so there's going to be a force downward, in other words, attraction. Okay. Now we have force per length is going to be equal to F over L, unit length. So I have I and I've divided through length by length, okay? So force per length. I have the B field, which is mu naught. I just erased it, it's fine. But the B field is I, so 1. The B field is mu naught I sub 2 over 2 pi A. So it's a product, and what do we have? Attractive. So I'll put note, attractive. So there's our force per length expression. 2 pi A. Force per length, all isolated here. So F per L U naught I1 I2 over 2 pi separation. And it is attractive when the currents are parallel, therefore it's repulsive if they're anti-parallel, if they're in the opposite direction. Attractive if parallel, repulsive if anti-parallel. That is to say, same direction or opposite directions, as we see right there. Okay, so this is important to see. It's a really basic application. We have good demonstrations of this. We actually build a device with these current carrying conductors, and then depending on the direction of currents we send through, they either attract or repel. So it can be done in a very controlled manner, so controlled in fact that if you send the same current, through the top and then through the bottom, you can use this force here to define the ampere. Okay? Because if you have ampere here and a Newton per meter, and you already know mu naught, and you can carefully measure these distances. By the way, to measure the forces, the way you do it is you put these conductors together in a scenario where there's a scale. So there's a balance on this thing, and therefore you can use them as the end of a scale, have very delicate force measurements. We used to have one in the department using a scale. Okay, let's see if there's anything else I have here. Yeah, I'll just put this as a note. By measuring forces and distances, you can use this to define the ampere. And use to define the ampere. We can use this formulation right here. Okay, good. So very important and elementary examples of a straight wire plays a big role. Now, if you want strong magnetic fields, though, you don't just have a straight wire, you do more, and that's what we're going to talk about next. What we do is we take a straight wire, take a wire, and turn it into a loop. Okay. So what we need next is the field of a loop of wire. Let's send this up here. Field of a circular loop of wire, always carrying a current. And once you have a single loop, you can wrap many loops and get stronger and stronger magnetic fields. So next, let's look at the field of a current loop. B field of a current loop. How am I going to draw this best? Yeah, imagine it's in profile here, so it's in and out of the board. There's the direction. Okay, we're looking at a loop on edge. And what we do is we use the same rule that we have for the infinite current, but we just imagine we're very close to this, and then there will be little concentric circles of B field, okay, going around the whole thing. if you're close enough, right? If you're close enough to a curve, it looks, you know, fairly straight. So the effect of this, of a current in this direction, is to have quite a few of these, and they all add up. So they're going to add up to B field going like this. And the amazing thing is, you end up with, you know, you've got this directionality to, remember, that's leaving a north pole if this were a magnet. You actually end up with a dipole field. So B field of a current loop is like a magnetic dipole. And you know, the magnetic dipole, if you had north and south pole on a magnet, you know, it has this property here, as we've seen before, okay? And it goes around like that. You're going to get the same thing here just by adding up all those infinitesimal elements. So that's really important. It starts to explain to us why we cannot ever isolate a north or a south pole, because this is an infinitely thin, right? It's just one ideal loop, and it's giving us a dipole field, and it just comes from a current. Okay. So what we do is go ahead and generalize this using our integral, which is no longer up there. I'll write it back up there. So the field of a current loop, it's like a dipole. And this shows us why you can't cut this magnet in half and then, you know, keep slicing it and isolate a north and south pole. It always has a south pole. There are microscopic currents at the atomic level that are actually producing the dipole field of the just chunk of magnet here. Good. So what we're going to do next is integrate up the B field of a current loop. That's our next project. And I should be able to get to the Helmholtz coils in that case. Okay, we'll send this up. Let's call this the magnetic field and it's going to be on the axis of this current loop. So let me set this up. We're going to have X, Y, Z axis. In the YZ plane is where we have our loop of radius r, and all of the little vector product circuit, you know, elements here are going to just give us a field at this point here pointing in that direction, okay, by our right hand rule. So we'll get a cancellation. We're just going to get dBx component if we're on the x-axis. We're not asking away from the x-axis, just along the x-axis. We'll have the mu naught over 4 pi. We want to integrate this thing up. Integral, I'll just say the circle of radius r ds. We'll pull the current out, of course. ds cross r hat over r squared. And again, I'm just going to go ahead and give the answer to this one and skip a page here, or go down to the bottom. In fact, it's not that bad because it's just the geometry here, and when we go around here, it's always the same thing. We just multiply by 2 pi r after we've isolated these expressions here. What we end up with is b sub x is equal to mu naught I r squared over 2 times x squared plus r squared to the 3/2 power. Okay, so I'm going to put this in a box. This is a result that we want to make use of. Okay. And yeah, use your right hand rule again. So ds aimed here, you know, your r hat is aimed at this point there, the ds with the cross product. You're only going to get resultants that point that way, because the other ones from up and above and below are going to cancel. So let's look at the limiting cases of this first. Namely, check at x equals 0. Then we've got r squared to the 3/2, so 1/2 is r. We've got r to the 3rd. We've got an r squared in the numerator, mu naught I over 2r. Okay. Same type of expression as we had before. Dimensionally, I mean, dimensionally. What about for large x? So this is the one check. Second check is for large x, much greater than the radius of the thing. Then you can neglect this r squared, and you've got an expression of square root of x squared is x, 1 over x to the 3rd. Now remember, 1 over x squared is like a field strength. 1 over x to the 3rd was like a dipole strength back when we were doing electric fields. So we also have the magnetic dipole strength going as 1 over x to the 3rd at large distances. Then b proportional 1 over x to the 3rd, just like a stand, you know, the dipole strength goes as 1 over x to the 3rd for electricity and magnetism. So good, we have that. And now I want to set up the Helmholtz coils. Oh, and yeah, in terms of the pole here, if you're on the left of it, the direction would be the same way, right? It's just like a north and south pole situation. Good, I want to set up and consult the clock here first. Okay, yeah, this takes about a certain amount of time. I want to set up the Helmholtz coils. There's a problem in the book about the Helmholtz coils. I showed them to you the other day. They're kind of important, and they will make use of this formalism. Helmholtz coils. Helmholtz coils are when you have the number of turns like this and you separate this object. By the way, this had a radius, capital R. I didn't write it in there. So you set up this kind of circular loop and then a second circular loop at a particular distance away from each other. And in fact, you separate them by their radius r. So the Helmholtz coils, I'm going to draw as the best I can here. We've got an x-axis, we've got a y-axis. We'll go, you know, when I think about it, my version may be a bit different than the book. Let me consult the text here. Yeah, I was gonna give this as a homework problem. Let's see, maybe I'll do it for you guys. Yeah, they put them at plus or minus. This is related, it's not exactly the same. Let's set it up. Okay. So first we'll set them up and then we'll consult the text, because I'm going to go with what I have here. Good, so what we do is we have coils here in this, this is X, this is Y, Z coming out here. And this is a radius R, I'll state that now. And what we do is we, at a distance R on the X-axis, we do a second set of those coils with as many turns as we want each, but the same number of turns. So the centers of these coils are separated by R. By a distance which is equal to the radius of the coils. I should have brought them back in here. R, got a 2, very good. So, this one's centered here, this one's centered here. We have Bx for the first loop, and then second loop. We have this expression right here. So we have u naught I r squared over this 2x squared plus r squared, 3/2 on the axis. Actually, let me do it differently. So we have 2 loops. I'll just write Bx total. So we need this field when this thing has been shifted over to the right by R, but that's no problem. We have u naught I r squared 2x minus r squared plus r squared to the 3/2, right? That's the same expression, just shifted over to the right by r like that. So that is B total. Better to put it that way from the start. First loop is this one, second loop is that one. How about that? Okay, so what's interesting about this is that at the center of these coils, namely at x equals r over 2, you get a very uniform field. And that's why it was used for that experiment I showed you the other day. And that's what we're going to prove. The B field is, I'll just write very uniform, considering where it came from, at x equals r over 2. And the way you prove that, all right, because you have dB dx at x equals r over 2 vanishes, right? So it's somewhat constant there, but also the second derivative at x equals r over 2 is also equal to 0. And you can even take a third derivative, I think, and show that it's equal to 0. So what that is, that's a property of the calculus here, that this function is very constant, right? The more derivatives vanish at that point, x equals r over 2, the more constant it is. And that's the idea here behind the Helmholtz coils. So just by manipulating the current, right, you can dial in, just by changing the current, you can dial in the strength of the B field here. That's what is going on in that demonstration I described to you last time. I couldn't get it to work here in the light, okay, but I did describe it to you in the last lecture. So yeah, the Helmholtz coils are a very interesting way to control the magnetic field, to produce one that does what you want. It's not just the not just the ends of a magnet. It's, it's being produced by the currents in here, and the region where the field is very constant, would be around here somewhere, constant field, and that's where you can do your experiment that requires a constant field. Okay, that may be as far as we get today. Let me consult. What I'll do now is write down some homework problems and say a couple words about them. This chapter has quite a bit of material coming up. But yeah, we'll get there. First, let's look at the homework problems. See what I've written down here. So homework 21, we are in chapter, not 26, we're in chapter 27. So homework 1, chapter 27. Let's see what we have here. Say a word about each one. I have 16, 23, 34, 38. 16, 23, 34, and 38. Let's see what I was thinking about. Yes, okay, 16 is a beauty. In fact, let's go ahead and erase this. We'll keep this. That was not, if you'd had the integral, it was b, not db. You may want to make that correction here. We were talking about b here because we had the integration. So I'll keep that expression up there. So here is a B field that we want to calculate, and it is of a hydrogen atom model in which the electron orbits the proton. Okay. So this is for 16. We've got a proton, which is a positive charge, and we've got an electron, which is a negative charge, orbiting the proton at some radius. So how can we do this here? We want to get the magnetic field according to this, and if you just do a ds cross r hat, say we do it here in the front, ds and the r hat towards the center, you'll see it's going to be pointing up. Okay, my perspective is kind of bad here, okay? But we're in the flat plane. So you just do your ds cross r towards the middle, and you've got a field that's pointing up, and it's pointing up at the location of the proton, okay? But how can we say that there's a current? Well, we have our length element. When we integrate ds, we get just 2 pi r, and we integrate around the circle. And the current, I is equal to dq over dt, where we have charge with respect to time. So how much charge is going around? Well, the dq is just the electron charge. What about the dt? Well, the dt is the time it takes to go around once. Okay. E over dt with v times dt is equal to 2 pi radius. Okay. So dt is 2 pi radius divided by v. And how much of that? Yeah, have a look at that. That's a good one. And then the direction I've already given and the magnitudes, all you don't actually have to do an integration right? It all comes out because we're right there at the location. So good. That's problem 16. Kind of an interesting problem. What else do we have? We have 23. 23 is the Helmholtz coil problem. So it's those derivatives that I'm talking about. Okay, you can do them this way. They say to set it up symmetrically on either side, but you don't have to do that. Okay, you can go ahead and do mine and do them at x equals r over 2, so it's already been set up. So Helmholtz and 34 and 38. 34 and 38 are just right-hand rule type problems. So I'll even show you 38. 38 is right-hand rule for currents. Yeah, so we have currents on the corners of a square. And we want to get the field at this corner. And all you really have to remember is that the B field, for example, due to this one, so 1, 2, and 3. If this were coming out of the board, then the B field for 1 would be here, B sub 1, right? If this one were coming out the board, then the B field would be like that. It would always be tangent to a circle drawn from here to the point where you're trying to measure the B field. So 38, 34 are problems along that type. They're really just a little vector addition, right-hand rule stuff. No big deal. Okay, good. There's a lot of interesting work to be done here. We still have a lot to do in this chapter, but we've made a good start. And we will see you next time.